Hi guys, so today I'm going to be walking through some vector stuff with you. Now most of this should be revision from National 5. Last week I set some revision vector questions. Some of you attempted those and I gave you some feedback. If you haven't had a chance to do that already or you're unsure, we'll go through it today and then you can attempt those questions that I set last week. I'll just remind you on Google Classroom where to find them. So we're going to be talking about vectors first of all, and then this week we're going to be moving on to equations of motion stuff. Again, some of it will be revision and some of it will be brand new equations and new ways of doing things. So first of all then, if we just do a bit of a recap as to the definitions of vectors and scalars. So a vector is a measurement that has magnitude and direction. So examples being force. If you push something with a force, it has a magnitude, for example 20 newtons of force, but obviously that force is then going in a direction, so that's a vector quantity. A scalar is a measurement that has magnitude only, for example distance. Now displacement is a vector, so some of you might have wondered what was the difference between a displacement and a distance. So it's all about the fact that displacement being a vector, it has a direction, whereas distance is just a scalar quantity. So let's look at this example then. So let's say you've got a racing car that starts off here, it goes round the track a distance of 240 meters and ends here. So the distance that it's gone, the total distance travelled, is 240 meters. So that's the total distance that the car has gone around the track from where it starts to where it finishes in. So that's quite simple. However, the displacement is the sort of distance and direction from where it starts to where it finishes, and that's the main difference between displacement and distance. So something, technically speaking, if it had gone all the way round to where it had started, obviously its distance would have been more than it is to start to finish line, because it probably would have had to have gone back again, but the actual displacement, so from where it starts to where it finishes, can sometimes be zero, because if it finished at the starting line, if it had gone back and finished there, then its displacement from where it starts to where it finishes would have been zero. However, in this case, we're just going from where it starts to where it finishes, and that is 40 meters north. Now, sometimes it will be, so north is a bearing of 0, 0, 0. We'll talk a wee bit more about bearings in a minute, but sometimes it's a bit more complex. Sometimes we have an example where we have to work out an angle, and also when we connect these lines, they make a triangle and use Pythagoras. So let's look at this then on a different screen. So a girl runs 40 meters east, then 30 meters north. So I've got it here. So what we're working out then is this part here, because this is, so the girl starts here and finishes here, so this is the displacement, okay? So the displacement is from where she starts to where she finishes. It's in meters, obviously. So we just use Pythagoras for this. So we'll just use that c squared equals a squared plus b squared, and we'll call this c, this a, and this b. So then if we just put those numbers in, so c equals the square root of, just rearranging that, taking that to that side, a squared plus b squared, and then if we put our numbers in, so a, so we've got 40 squared plus 30 squared gives us c. So that's the first part of working out the displacement then, so we just put that into our calculator, so 40 squared plus 30 squared, and then all square rooted. So we end up with 50, and some of you might have noticed that it is a 3, 4, 5 triangle, so that was always going to be 50 without us doing it, but we'll just doing it as a process. So 50 metres, so the displacement is 50 metres from start to finish. However, that's only part of the story. Because it is a vector quantity, we need a direction as well. So the direction in this case is an angle or a bearing. So first of all then, if we do to keep us right with our angles and bearings, if we just do a simple north, east, south and west, so what we're doing is working out the direction that the runner is going in as a bearing. So if we imagine then that she starts here and this is north, you can see that she's going in a northeast direction. So if we was to draw this part on here, she's going in a northeasterly direction, but at what bearing, so at what angle? So first things first, we need to work out this angle here. Once we've got that, then we can work out what the bearing is. So to work out the angle then, we're going to use SOHCAHTOA. So just to write this out, just to remind us. So we've actually got all three sides. We could use any one. I'm going to use tan. So tan of my angle equals my opposite, which is the opposite one to the angle. So we come right across here, that's 30, divided by the adjacent, which is this one here. Obviously this is always hypotenuse, so divide that by 40. So we end up with tan theta equals 3 over 4, which is 0.75. Rearrange that, so we do tan to the -1, 0.75. Put that into our calculators. Our angle is 36.7 degrees. We could just round that up actually to 37 degrees. So this bit here is 37 degrees, but if we look here, that is 37 degrees. But in terms of a bearing, our bearing is from north all the way around. So if you look here, this point here is actually our bearing. So to work that out, if you imagine that this quadrant is 90 degrees, so it's from north to east is 90, and then another 90 from east to south, another 90 from south to west, another 90 from west to north again, because the whole thing is a circle, which is 360 degrees. So each quadrant equals 90 degrees. So if we just take then our 90, take away our 37, so 90 take away 37 gives us 53, and our bearing is always as 3 figures, so 053 is our bearing. So the total resultant displacement from where she starts to where she finishes, she goes 50 meters at a bearing of 053 degrees. So going back then, just to double check, that's fine, that's correct. So 50 meters at 053. I will post the spreadsheet, sorry, the PowerPoint on Google Classroom, so you can actually have a go or have a look through this at your own leisure. But I just thought I'd just do a wee lesson on it. So now we come on to speed and velocity. So as with distance and displacement, you've got the distance, which is the scalar version of how far something's travelled, displacement, which is the vector version. We have exactly the same thing with speed and velocity. So again, speed is distance over time, so you use the scalar version of it, so you would always use distance over time. Time is obviously a scalar as well. So speed would be distance over time, whereas velocity is displacement over time. So if you then come back to the same problem, so we've got that the girl runs 40 metres east and 30 metres north. She does this in 50 seconds. So what is her average speed and what is her average velocity? So to work out speed, we use distance over time. Now the distance that she's travelled, although from point A, point B directly, it's 50 metres. In fact, she's actually doing 40 metres and then 30. So in terms of the total distance she travels, it's 70, because she goes 40 metres, then she goes 30. So if we use that then, so we use the distance for speed, so 70 metres is her distance, divide that by 50 seconds, that tells us that her average speed is 1.4 metres per second. However, for her average velocity, we need to use the vector form, which is the displacement, and we do displacement over time. So our displacement, as we've worked out before, is 50 metres. So if we do our 50 metres divided by our 50 seconds, she has an average velocity of 1 metres per second at 0.53 as a bearing, because again our velocity has to have both magnitude and direction. So in terms of at higher then, the only difference with vectors at higher physics is that you need to be able to add vectors in non-right angled triangles. So there are a couple of ways of doing this. The first way is by doing a scale diagram. So you'll need a ruler and a protractor for that, and obviously squared paper is the most ideal. The other way is to do it using the cosine rule. Now if you are doing higher maths, this might be the one for you. If you're quite happy using the cosine rule, that's fine. You will be given the cosine rule in the exam, for the higher physics exam, because you get a separate formula sheet that has some maths formulas on it as well. However, if you're not happy or not comfortable doing that, or maybe even just at this stage, then you can use a scale diagram. So an example is here then, so you guys can just look at this in your own leisure, but I'll just briefly run through it. So if we're not working with right angles, let's say that a runner runs 400 metres north, then 500 metres east. So it goes 400 metres north, then 500 metres northeast at 45 degrees. So obviously if it's going northeasterly direction, secondly, then it's not at right angle, it's not coming along here on the east. So this would be 500 metres at an angle of 45 degrees, so you'd have to draw that with your protractor, and you'd need to work out the resultant displacement. So you can use a scale diagram, or you can use the cosine rule. I will put the cosine rule in at the end of this video, just so that you guys have it, and you can maybe try it with both ways. It's up to you, it's up to what you've got at home. If you've not got a protractor, then the cosine rule is probably the best way. So that's how you would do it then if you don't have them at right angles. So other than our first problem was in terms of displacement, this you can also do it for velocities. So if you've got something travelling north or flying north with velocity of 280 kilometers per hour, and then you've got a wind that's blowing from east to west, so it's actually going to obviously affect the direction of the plane, so it's going to kind of push it along this way here. What you can do is work out the resultant velocity because of this wind, and it's exactly the same process using Pythagoras, it's just that you're dealing with velocities and not displacements. So again, you can have a wee look through this one here. It's the same process, and you can work this all out to have a resultant velocity of 286 meters per second at a bearing of 348. If you're wondering where the 348 comes from, if you imagine you work out this angle here, if you were to put that triangle in this quadrant here, you can see you've got your 90, 180, 270, 360, and then our angle is actually in this part, so whatever that angle is here, it's 360 take away that angle, and that is what gives us 348. Because it's 360 take away, you've just got that sort of 12 degrees in this part here. Obviously the 12 degrees comes from using trigonometry to work out the angle here, and that's 360 take away that angle gives us a bearing of 348. Now, force vectors are a common vector, sort of working out force vectors is quite common to hire. So for that, you need to know if you've just got an angle and maybe a resultant force, because in these other examples we have to work out the resultant force. If you have the resultant force, so for example, if you're applying a force at an angle, you know what the force is, you know what the angle is. Sometimes you have to work out what the horizontal and vertical component of the force is. And I'll give you an example in a wee second of that. But if you've got F here, so you've got your resultant force already worked out and you've got your angle, if you look at it from the point of trigonometry, to work out the horizontal, it would be F cos of theta, and for vertical it would be F sine of theta. The reason being, if you was to work it all out, I can show you in a wee second how you would work it out, or you can just remember this. Obviously it's cos for the horizontal because it's sort of adjacent to it, and sine is because it's opposite. So the vertical is F sine theta and the horizontal is F cos theta. So let's give an example then. Oops, that's okay, it's actually on here anyway. So if we come up here, let's just get rid of all that stuff. So we've got a strong man that pulls a car with a force of 1,240 newtons at an angle of 30 degrees to the horizontal. So we've got a little picture here which helps. So if you just draw, obviously this is our horizontal reference point, which is the ground. We've got he's making an angle of 30 degrees, and then the car is here, and that's the rope that he's pulling with, and the force is 1,240 newtons. So as you can see, we've got an angle and we've got our resultant force. So what we need to do is resolve it into the horizontal and vertical plane. So part A then is calculate the horizontal component of his pulling force. So horizontal, because we're adjacent to the angle, it's F, which is obviously 1,240, F cos of theta, and our vertical is F sine of theta. So F cos of theta equals F, which is 1,240, cos of 30 degrees. If you put that into the calculator, you get 1073.9 newtons, which you can just round to 1073.74 newtons. So that's the horizontal component of the force. Part B, it says work out the frictional force on the car. Now, if you go back to the question, to the extra bits of information, it says that the mass of the car is 800 kilograms and it's going at a steady speed of 0.5 meters per second. If something's traveling at a constant speed, it means that forces are balanced, because forces, if they're unbalanced, cause acceleration or deacceleration. But we know it's a steady speed, so if it's a steady speed, it means no acceleration. If there's no acceleration, forces are balanced. So if he is pulling with a force of 1074 to the horizontal, if we just label our forces on the car here, so that is the horizontal component of the force, 1074, which we've resolved before. That's our rope. Then it must mean that the equal and opposite force is 1074 newtons. So the frictional force is 1074 newtons as well, because we've got balanced forces. And then part C is the work done. So work done, or EW, as you'll see it in the formula sheet, is force times distance. So again, we work out the force, which is 1074, times a distance of 500 meters, and that gives us 1074 times 500, 537,000 joules, because work done is a type of energy and energy is measured in joules. So that is how you do that question, and this kind of helps us to understand why it is we need to resolve them into horizontal and vertical forces, because although we've got a resultant force here, when it comes to things like friction, balancing forces, to work out the frictional force we had to know what the horizontal force is. We didn't actually need to use the vertical one in this question, but sometimes you need to use that as well, and we'll be looking into that further along the course. So practice the vector questions if you haven't done already. If you have done, I'm going to put some other questions up on equations of motion. Again, the first part should be revision, and we'll be going through later in the week some equations of motion stuff as well, the sort of new higher stuff that you've not covered before. Hope that's okay, guys. Please message me if you've got any problems, and I will post the work for this week a wee bit later on.